Welcome to class number 6, session number 4. In the current session, we will present some advances that are based on semiconducting nanowire sensors for gas sensing applications. The application of silicon nanowires as gas sensor face many challenges. Among the rest, this nanowire suffers from high density of surface states at the silicon oxide and silicon interface. The presence of native silicon oxide at the silicon nanowire surface is responsible for interface states that lower the sensitivity of the field effect transistor device when used as sensor. In addition, the silicon nanowires that are used or utilized as gas sensors suffer from high density of trap states at the air silicon oxide interface. In this case, the presence of the native silicon oxide at the silicon nanowire surface is responsible for the surface trap states that cause the so-called hysteresis phenomenon, namely a lag in the response obtained in the forward and backward electrical scans of the source drain current versus backgate voltage. Functionalization of the silicon nanowires oxide sheath by a monomer of trichlorosilane molecule throughout the silicon-oxygen-silicon bonds is a simple and cost-effective approach to remove trap states and the associated hysteresis effect. As shown in scheme E in the left, to enable silicon nanowires to sense volatile organic compounds or gas analytes, the silicon nanowire shall be modified with dense hydrophobic organic monomer such as hexyl trichlorosilane that is presented on the screen. The left figure shows dark field optical microscopy image of a representative silicon nanowire field effect transistor. The silicon nanowire was bonded in this case with two gold source drain electrodes and formed a 2 micrometer conductive channel. TEM image that is seen in figure number C shows that the silicon nanowire has around 5 nanometer native oxide on its surface. The right side figure shows linear scale and logarithmic scale of current source drain versus backgate voltage. And this is done for various concentrations of octane and decan as well as dry air as a baseline. The observed current between the drain and source at high negative backgate voltage is almost equal to that of the current between the drain and source in the air. The drain source current systemically decreases upon applying positive gate voltages and decreasing the volatile organic compound concentration. Furthermore, voltage threshold, which abbreviated as VTH, and Hall mobility, which are extracted from the extrapolation of the linear part of the current between the source and drain versus the backgate voltage curves, all linear increases with the volatile organic compound concentrations in this case. In this system, the gas analytes, or the volatile organic compounds adsorption, induce conformational changes in the organic monomer and affects the dielectric constant. In this case, the effective dipole moment of the organic monomer or the charged surface state density of the silicon oxide monomer interface are changed. These effects in turn change the conductivity of the silicon nanowire quite effectively. As a complementary part of these findings, researchers have studied the hysteresis of the silicon nanowire field effect transistor that is modified with the triethylamine that is associated with the trichlorosilane modification and with also direct trichlorosilane modification, as well as bare silicon nanowire field effect transistor that is having high as well as long concentration of hydroxyl groups on the surface, which are the main source for the hysteresis. The figures on the right side on the screen shows logarithmic and linear characteristics of the silicon nanowire field effect transistor that is scanned forward and backward against different conditions. As seen in the figure, sensors that have high concentration of hydroxyl groups on the silicon nanowire surface exhibit hysteresis of around 15.7 volt. This hysteresis is reduced almost completely to about 0.8 volt after modifying the silicon nanowire with controlled assembly of hexyl trichlorosilane. These facts suggest that there is a critical effect on the hysteresis of the gas silicon nanowire sensors that is made by the passivation of the hydroxyl groups that are found on the silicon nanowire surface. The FET characteristics of the controlled assembly of the hexyl trichlorosilane as a comparison is reasonable after and reproducible after 6 months more or less, and has shown a change of around 5% drift only after this period. The passivation of the surface states and the elimination of the hysteresis effect with the help of advanced molecular layers can lead to improved sensing performances. The presented figure summarizes the conductivity change that is calculated for the same hexyl trichlorosilane silicon nanowire field effect transistors prepared by the so-called controlled assembly. And this, of course, is schematically presented towards various polar and non-polar volatile organic compounds, or briefly gas analytes. As could be seen in the figure, all polar volatile organic compounds show a non-zero positive conductivity change at high negative voltages and the maximum close to the base voltage threshold. In contrast, the water molecules show a non-zero negative conductivity change at high negative voltages and a minimum close to the base voltage threshold. The sensitivity of the hexyl trichlorosilane silicon nanowire field effect transistor towards non-polar volatile organic compounds exceeds the sensitivity towards polar molecules. This behavior could be attributed to the formation of a dense hexyl trichlorosilane monomer that acts by transferring the recognition event of the non-polar volatile organic compounds to the silicon nanowire while preventing polar molecules from reacting or reaching the silicon nanowire surface. In support of this claim, we have observed negligible responses of the bare silicon nanowire field effect transistor sensors upon exposure to non-polar volatile organic compounds, and non-stable and non-reproducible responses upon exposure to polar volatile organic compounds. In spite of these improvements in the use of molecule-terminated silicon nanowire field effect transistors for gas applications, the mutual relationship between the molecular layers and the volatile organic compounds or gas analytes is still a puzzle. With this in mind, researchers have tried to explore the effect of molecular layer functional groups on the sensing properties of the polar and non-polar VOCs. For this, silicon nanowire field effect transistors are modified with tailor-made molecular layers that have the same backbone but differ in their end groups. These functional groups can be divided into two main categories. electron donating groups, such as the monolayers with the methyl and the benzene end groups, and electron withdrawing groups, such as the monolayers with the carboxylic acid and the carbomethoxy groups that appear at the end of the monolayer. This slide shows sensing responses of a silicon nanowire field effect transistor sensor modified with carboxy methoxy functional group molecular layer upon exposure to octanol as a representative example. When exposed to octanol, the electrical curve shifts to the right, and in this case, the higher the octanol concentration, the larger are the shifts of the electrical curves. To further investigate the sensing responses, the voltage threshold and the Hall mobility are extracted from the extrapolation of the linear part of the electrical characteristics that are shown on the screen. Meanwhile, the on current over the off current ratio, which is defined as the ratio of the current at backgate voltages between minus 40 volt and plus 40 volt in this case, is also calculated. Then, all these parameters that are extracted from the silicon nanowire field effect transistor device are plotted as a function of time, as shown on the screen. As shown on the screen from the figures, exposure of a sensor to octanol shifts the V threshold, or the voltage threshold, to higher positive values. The higher the octanol concentration, the higher is the voltage threshold upon exposure to octanol as compared to the dry air or as compared to the baseline. The sensor response is rapid, fully reversible, and responsive to a wide variety of concentrations. In the presented schematics and results on the screen, one can see that the Hall mobility at the I on over I off ratio shows similar behavior to that of the voltage threshold. To compare performance of sensors with different functional groups to volatile organic compounds at different concentrations, the different field effect transistor parameters between the volatile organic compound exposure step and the dry air exposure step are calculated. As the volatile organic compound concentration increases, the voltage threshold changes of sensors are increased. Silicon nanowire field effect transistors that are modified with different functional groups show different voltage threshold change towards exposure to the analytes of interest. Upon exposure to a specific volatile organic compound, carboxy-methoxy silicon nanowire field effect transistor show the strongest change in voltage threshold, followed in succession by methyl-terminated silicon nanowire field effect transistor, and then by benzene-terminated silicon nanowire field effect transistor, and finally by carboxyl-terminated silicon nanowire field effect transistor. As could be seen in the presented figures, the functional group types determine the voltage threshold shift direction. Upon exposure to VOX, the voltage threshold of sensors with electron-donating functional group are shifted to the left side, namely they give negative response. In contrast, the voltage threshold of sensors with electron-withdrawing functional group are shifted to the right side, namely those which give positive response. All sensors, part of which are shown on the screen, show positive response in the Hall mobility change. And this is, of course, upon exposure to the various volatile organic compounds. Also, one can see that the Hall mobility changes of most tested sensors increase with the increasing the Vogue concentration. Amongst the tested sensors, methyl-terminated silicon nanowire field effect transistor show the strongest Hall mobility responses upon exposure to all tested volatile organic compounds, followed in succession, in this case, by the carboxy-methoxy terminated silicon nanowire field effect transistor, then carboxyl terminated silicon nanowire field effect transistor, and finally by the benzene terminated silicon nanowire field effect transistor. As seen on the figure which is presented on the slide, in addition to the exploration of the effect of the functional groups on the sensing of the silicon nanowire field effect transistors, researchers have also explored the effect of the chain length effect on the gas sensing of the silicon nanowire field effect transistors. Here, the molecular layers have similar backbone and functional group, but differ in their alkyl chain length, namely from chain length that range from C5 to C6, C9, and C11, as seen in the schematics. As seen in the presented results on the screen, all sensors shows negative response to the tested volatile organic compounds at all applied concentrations. In particular, the voltage threshold responses of all applied sensors show volatile organic compound concentration that is dependent on the character for polar volatile organic compounds. That is, the higher the volatile organic compound concentration, the higher the voltage threshold change, and also the voltage threshold change of a given sensor on exposure to different polar volatile organic compounds show a decreasing trend as the volatile organic compound chain length increases, except for the case of C11 monolayer, which show the highest response to octanol. Compared to nonpolar volatile organic compounds, the sensor response to polar volatile organic compounds is higher than the nonpolar counterpart that has the same carbon chain length. The silicon nanowire field effect transistors that are terminated with a series of different chain length monolayer show a positive response in the Hall mobility at all applied concentrations of the gas analyte. At low concentrations, the longer the nonpolar analyte chain, the higher the Hall mobility response of the C5 silicon nanowire field effect transistor and C9 silicon nanowire field effect transistor. However, the C6 silicon nanowire effect transistor show nearly the same response when exposed to nonpolar analytes in the gas phase. In addition, the C11 silicon nanowire field effect transistor don't respond to nonpolar analytes in the gas phase because of the large standard deviation of the signals. On exposure to polar analytes in the gas phase, the sensor responses of all applied sensors increases with increased volatile organic compound concentration. In this case, the Hall mobility response of a given sensor on exposure to different polar VOCs, or volatile organic compounds, show a trend to decrease as the volatile organic compound chain length increases. In addition, exposing a sensor with a specific functionalization and to a specific volatile organic compound concentration result in higher changes in Hall mobility for polar analytes in the gas phase than that of nonpolar analytes in the gas phase as well. All in all, the interaction between the molecular layers and the volatile organic compounds can be classified to three main scenarios. The first scenario is that the dipole-dipole interaction between the molecular layer and the polar Vox are established. Secondly, induced dipole-dipole interaction between the molecular layers and the nonpolar Vox. And finally, molecular layer tilt as a result of the volatile organic compound diffusion. When the volatile organic compound absorbs on the molecular layer surface, the volatile organic compound is attached to the exposed functional groups. Therefore, the alignment of the volatile organic compound on the molecular layer surface is controlled by the properties of the molecular functional groups. For instance, methyl and benzene functional groups are electron-donating groups. In these cases, the volatile organic compound's negative pole is attached to the molecular layer's surface. Under these circumstances, the dipole moment orientation of the adsorbed volatile organic compound is similar to the molecular layer. And as a result, the adsorption of the volatile organic compounds increase the absolute value of the molecular layer's dipole moment. Since the dipole moments of the various molecular layers are negative, voltage threshold shift to negative side are obtained. Furthermore, the large intermolecule space of the long-chain molecular layer, which is due to the longer chain length of the molecular layer and due to the low second layer amide interaction ratio, enable it to adsorb more gas analytes than the short chain molecular layers, and thereby this increases the voltage threshold response to the gas analytes that are examined. In addition, it's likely that the diffusion of the gas analytes into the molecular layer, determined by the type of the functional group, is the main reason for the whole mobility responses. In summary, the chemical reactive surface of the silicon nanowire provides a powerful platform to modify the various organic molecular layers and therefore enable silicon nanowire field effect transistor sensing to various analytes in the gas phase. We now have reached the end of class number 6, session number 4. Thank you.